Hi, my name is Simon Crosby. I am CTO at Swimus AI, and I'd like to spend some time talking to you about how to deliver continuous intelligence from Apache Pulsar event streams. Everything I'm about to tell you is open source. It's licensed under the Apache 2.0 license, and you can find it at swimos.org. So it's a platform which allows you to easily build applications that could deliver intelligence from data as it flows. And let's dive into that. So in the spirit of telling you everything in the talk in one slide, SwimOS is a stateful real-time Apache Pulsar stream processor that takes care of everything an application might need, including clustered and distributed operation. So it builds a peer-to-peer mesh of instances which scale an application and deliver compute as it needs it, for example, on Kubernetes. And then at the application layer, it builds a distributed graph of what we call web agents, which continuously compute as data flows over the application graph. The graph is built dynamically, and the relationships between elements in the graph are fluid and based on what we find in the data or what you declare. So SwimOS builds and scales applications from event data, creating a big distributed in-memory graph that computes as data flows. It automates distributed application execution, and it converts streaming data into streaming insights. It load balances, secures, persists, and auto-scales applications. They're very easy to develop because they're simply extensions to Java. And it delivers unimaginable performance because it is entirely in memory. Gosh, there is a lot of data out there. So the small town of Palo Alto, California, in Silicon Valley, has a few hundred traffic intersections, which together deliver more data per day than Twitter. And that's a lot. Now, Las Vegas delivered 10 times the size of the Library of Congress digital archives every single day from about 5,000 intersections. So there is a huge amount of information out there, and it's extremely expensive to store and then process later. More importantly, that's not really useful for many tasks that we have in mind. So let me tell you about an application which has to deal with a Facebook's worth of data every day. And this is probably the largest Apache Pulsar implementation in the world. And it's run by a large American mobile provider. This application syncs about 4 petabytes, that's 4 times 10 to the 15 bytes of information per day. It continuously monitors call quality or connection quality for hundreds of millions of subscribers and allows the provider to optimally assign its capacity to different users. And at any level of zoom, it continually provides insights into the current operation of the network, and it can find faults and dynamically assign capacity to those users who are affected by faults and outages. So this kind of application is indicative of the vast scale of information that we're going to be facing from applications in the future as more and more of our infrastructure products and so on are instrumented. And it's also indicative of the fact that this store and analyze approach just doesn't work. First of all, 4 petabytes is too much to store, but more than that, the data value itself is short-lived and the flows of data are boundless. There is no point trying to solve a customer's problem tomorrow when they're disconnected today. And by the way, the data just comes in an unceasing storm. Moreover, it's very expensive, it's slow, and it's mismatched with current business needs. So What are we able to do? We're able to reduce the customer's costs by 90% by keeping everything in memory. We're able to reduce the time within which they can get insights from about 10 hours to about 10 milliseconds. That's 1,000,000 times faster. And we can do this on the fly by simply inspecting data as it flows. So I'm going to show you how. But if you take away one thing from this talk, take this away, that this notion of big data, which is heavily predicated on the store and analyze notion, is really out of date. And we have to begin to analyze and react to data as it flows. And then if you really have to, or you really want to store the raw data, then do it later. Okay, so analyze and react on the fly so that your applications can run CPU speeds, not at disk and database speeds. So what is continuous intelligence? It is really qualified, I think, by 3 key factors. First of all, applications like this always have the answer. They don't have to go away and think and come back to you with an answer later when a UI refreshes or when a user query is entered. Okay, they compute the moment that they can. They're always computing. They analyze, learn, and predict on the fly. And there are big, quite substantial changes we have to make to the algorithmic structure of applications so that they can compute on boundless data, so that they can learn in an unsupervised way and predict their futures. But the fundamental thing here is that data flow drives computation as opposed to users consuming the insights. Okay, and that is a fundamental property of Swim. So let's get back to another example. I have 2 more. The traffic in Palo Alto, California is, it's pretty modest. There are a few hundred intersections, and every single one of these intersections continually predicts its future behavior and streams those predictions directly to consumers like Uber or Google or Lyft or whatever, so that they can better utilize the city infrastructure and route their vehicles through a city. So I want to point out here a key thing. You don't care that the light was green last Tuesday morning at 9:07 and 13 seconds, but you really do care what it may do in the next 2 minutes. Okay, and so this notion of continuous analysis, learning, and prediction is fundamental. The past is summarized into a learned capability, and the future depends on that. Let me give you another set of examples. We did a lot of work on traffic, all modes of traffic in Dubai. Here is some interesting computations which we need to perform. Find all trucks that are in or approaching a banned area. Maybe there is a festival underway. Or find trucks with bad braking behavior and alert the nearest inspector. So this notion of with bad braking behavior is dependent on every single GPS update from every single truck in the entire city. And so as data flows, we have to reevaluate it for every single truck. But the notion of nearest inspector is a geofencing operation. And the key thing I'm trying to point out here is that the relationship of nearness is very hard to capture in a traditional relational database. So the benefits of our approach, and we're going to get into how in just a sec, you can go 1,000,000 times faster. Okay, and that's merely giving you back Moore's law, because every time you reach out to a database, you're going slowly. You can use 90% less infrastructure because you do not have to store data and then analyze it later, hauling all of your data back over a network or back into memory. Applications in this world are very easy to develop and operate, and I'm going to show you how, because that I think is a big challenge. And one of the amazing and coolest things with this approach is that once you have this model, which is in memory in a distributed model formed by Swim, you can do data science on live data instead of having to do data science for data on disk. So let's dive into that. I just want to hammer home a key thing. To execute an instruction on modern CPU is about a nanosecond. Okay, cool. Let's call that the speed of an F-18. Well, this is what your cloud is like. Okay, it's like a snail. It's about 20 million nanoseconds to get a megabyte off disk. And if I ping US West to US East, it's about 80 million nanoseconds. What the heck are we doing, people? Okay, so the cloud is fabulous at going wide. That is, I can scale wide, and REST and databases have helped a lot there. But they're very poor at per event latencies. Okay, so we definitely do not want to adopt this approach where we effectively throw away the last 5 generations of Moore's law. Now, I want to draw a distinction between what we do at Swim and, say, Pulsar. Event streaming is cool stuff. We have all this data arriving into topic queues at our broker, and then Lambdas, typically stateless Lambdas, consuming from that queue. Often there's a database in the middle and then some application. Now, what's the problem with this architecture? First of all, we don't know how many Lambdas we should have because we don't know how many publishers there are. And so that ability to scale compute on the fly is very difficult. Second, we're dealing with databases, which means we're slow. And third, the application is idealistic, right? Somebody has to compute it sometime. So perhaps it's a GUI. So we're computing some analytics, which go and retrieve data from the database, do something in the model, and hey ho, draw some graphs on the screen. But what if I'm actually trying to compute something from my data, right? So I've shown here complex functions associated with each of my axes in this graph. And the key point is I'm trying to relate multiple different event types, event sources, to look for things like correlations or other relevance, which might indicate an emergency. What if the model is such that this particular system in practice doesn't behave like the real world or doesn't behave like the ideal world, and I'm learning the model on the fly for how this particular system would work? Okay, so the broker type approach and this idea that Lambdas will somehow show up and get events off the queue is fabulous, except for the problem that leaves the application architecture driven by end users, consumers of the data or the insights. So in summary, brokers are great at event infrastructure, but they don't run apps, okay? And Swim is all about running the apps. Now, I often get people saying, hey, cool, I can do that with a smarter database. You know what? There are lots and lots and lots of databases out there. And you can't blame database projects for trying to put more and more under the hood. But the problem is this, that databases don't find meaning or build models. You declare a schema upfront, okay? And what we need to be able to do is find meaning in data that's streaming. So for example, going back to my truck, when a truck has bad braking behavior and it's near an inspector, then tell the inspector in real time, okay? We can't find meaning. So the notion of a graph is very appealing. And so something like, Neo4j or whatever is very, very appealing. But again, these structures are typically held in databases. So graphs are good, but we don't want to have to go to disk. The relationships between things in the real world are very fluid. So going back to my mobile provider, devices predict where they might be relative to base stations. Cool beans, These are very, very fluid real-world relationships, and we need to be able to adapt. Databases don't analyze or learn or predict. They store stuff. They store stuff based on some model, but they can't find meaning and then learn based on that. They're very poorly suited to streaming data. This notion of an asset property, which is built into every database engine, is way too heavyweight for a model of real-world data where the update properties of any particular row in a database, that is the need for atomicity, is dealt with very, very, very simply without the need for all the heavyweight structure of distributed transactions. In the real world, the notion of truth is not always clear. So often devices are giving us estimates. Often we're sampling. Often we're building distributions to learn and predict. And so the notion of truth, as you might find in a relational database, a truck has an engine, is not necessarily valid here. Time is always fundamental. And a single event stream is not useful in many applications. So what we want to do is look across event streams from different things and find correlations, which can be profoundly useful in understanding what's going on in the real world. So time is fundamental, not just for ordering. So time series databases, yeah, big deal. They can order things based on time. It's not important and not very useful. Relationships between things are dynamic. So truck might be out of range of an inspector or entering into range. They're mathematical and they're geospatial. They could be predicted to be within a certain range, for example. And in this notion of a graph, we see that a single event, for example, a truck braking badly, could cause cascading reevaluations. For example, is this truck near this inspector or that inspector? And these must be done in real time. Fundamentally, databases don't run applications either. So Swim adopts a model, which is, I guess, a hybrid. It's fundamentally stateful. And so you see my notion of a lambda being stateful here in the sense that it can both scale up and out. So up, obviously, because we can have little models of things, but out because Swim manages a big distributed graph of stateful entities. These are called web agents, and they are little actors, if you understand the actor paradigm. When data arrives, we compute. Okay, we don't rely on data, on user interfaces or analytics interfaces or queries to compute. When data arrives, we drive computation from that arrival. Okay, and then we build a graph in memory on the fly, which understands and finds relatedness of things to establish meaning. And that is profoundly useful, for example, by finding simple things like correlation or prediction. Okay, and I'm going to describe to you how we can use languages and operations tools that everybody knows today. In our case, Java. Okay, so what's the big deal with Swim? I'm going to describe it in terms of SwimOS. Remember, you can get everything at swimos.org. Swim creates a stateful concurrent object called a web agent, which you can think of as an actor if you know Erlang from the 60s. If you know Akka, it's an actor there, but we don't use message passing, okay? I'm going to describe that in a sec. So we have bazillions of stateful concurrent actors, one for each data source, that continuously and statefully analyze data from a real-world sibling. Okay, so each one of these things is related to one real-world source. Okay, each one of these web agents dynamically links to related things. Now, how do we find relatedness? Well, we find it in the data, but we also find it based on the object model, which the application programmer describes. So, for example, this intersection, which is a logical thing, the web agent for it is linked to its neighbors. And linking has this amazing property, which allows us to track complex relationships. Now, linking could be something simple like containment. For example, an intersection contains maybe 80 or 100 sensors, but it could be much more complex. It could be computer relationships like correlated to or predicted to be within. And linked agents can see each other's state, and then they can continuously analyze, learn, and predict using their own state and the state of everything they're linked to. Okay, and then they stream their insights to other applications, to UIs, to storage, whatever the heck you want. Okay, and Swim contains a powerful set of web-based extensions which allow real-time updates into web-based UIs. Okay, so let's crack those topics open in a little bit more detail. Web agents are actors. They're stateful, concurrent, and distributed. I'm not going to cover much about distribution, but the name web agent should give you a clue. Every object has an ID, and the object ID is a URI. And as these things move around, and they do move around at runtime, Swim moves them, they move in a way where we can always find out where they are because they have a URI as their object ID. And so even as the graph moves between locations computationally, we can always keep them in sync. These web agents have lanes, and lanes are object members, but they're extended beyond just being state to also include code. So they're methods, basically methods and state. And they stream their updates over links. So you could see in this diagram a bunch of noise arriving at the left, or some noisy data stream, and it devolves into, say, for this intersection, or this light red and green, or there is a car present, or whatever it happens to be. But if something links to that lane, another intersection, say, or a UI, it is continuously informed every single time the state associated with the lane changes. Okay, and so we build a graph based on links in memory and in real time. Okay, so one could think of web agents also as stateful lambdas. You can imagine a graph or a query. Maybe a good analogy for this would be something akin to a materialized view in Amazon a Redshift. A web agent can analyze millions of concurrent updates to agents it's linked to. So we could have something which is analyzing traffic at national level, say, okay, in the US, and it is continuously receiving updates. Those can be debounced to allow bursts of state changes. Every time an update arrives, we invalidate the outputs that depend on it, and they can be time triggered or data triggered in terms of reevaluation. And then every once in a while, or as you decide, compute happens and the new state is directly streamed. So these are stateful lambdas which can perform the effect of, I guess, column operations in database at massive scale. Okay, what can web agents do? Well, Swim contains a powerful library of components which allow web agents to do awesome things. In particular, there is a capability for a web agent to build dynamically a DNN, feed it samples, and learn and predict. I'll cover that in the next slide. A web agents can continuously map reduce They can perform complex graph queries, and I guess they could do things with stuff like a SQL variant, which a long-running SQL variant. They can perform complex analysis, and there is implementation of algorithms like sketches. If you want a reference, I would refer you to generally the topic of statistical data structures. And of course, they can hook up to anything else. So for example, they could feed RDDs directly into Spark. But more interestingly, and of late, we have found a number of customers directly hooking this up to something like Jupyter Workbench. And so here you can create new analytics, you can query and analyze real-time streaming updates from millions of, or even hundreds of millions of web agents, and then push new analytics into this graph on the fly. It's very cool. So just an example for you, how might these things learn and predict? Well, going back to my use case of traffic, every single intersection, every web agent which represents an intersection, continuously forms an input vector from its own sensors and those that it can see, which are the states of its neighbors. Okay, how does it find its neighbors? Well, using Latin long. And throws that through a DNN. Now, on day one, the DNN has random weights. And so the first time through, it's just a guess. What we get is a predicted future state of the intersection. And then we have the luxury of time and watching what actually happens. And that gives us the difference, which can be back propagated. Okay, and if we go around this loop a bunch, then the weights either stabilize or they would diverge. But simply watching this delta, we can see whether the system is in good shape. And if it is, we're in great. We can use the model which has been built for us. I realize here I haven't dealt with time, and this is a complex and deep topic. Feel free to ask me questions after the presentation or indeed by email. Okay, so a Swim application is actually an in-memory distributed active graph. So it's pretty easy to build web agents, each of which contains some number of sensors, but a very simple additional piece of information, which is that they all report their latitude and longitude, allows them to find their neighbors. It's a very simple geofencing operation. And geofencing then allows them to share state. So the application itself is a graph in which there are hundreds or thousands of independent DNNs, each of which is predicting the future of a single intersection. And these things continuously stream their outputs to whatever subscribes to their feeds. So it could be a UI, it could be Uber, and we could be pushing directly into their Kafka. Okay, so Swim applications are computational graphs that compute as data flows. They're not based on, they don't require users sitting in a UI, and they're not fundamentally analytics based, and the analytics being manager, human level, top-down views. These are systems which continuously compute and statefully represent a changing world. How do we make it easy for devs? Well, Swim is just a set of extensions to Java. It deploys just in the JVM. Typical Swim code base is about 2 megabytes in size. So we deployed the same code in every instance. So the developer is simply writing a Java-based object-oriented program. Swim uses that program and the streaming data to build a stateful graph of these concurrent web agents, these little actors which represent real-world things, one per source. And these then link to each other to represent relationships like adjacency or near or whatever it happens to be, and to allow them to share state. And then as data flows from the edge, from the sources, They continuously compute by analyzing, learning, and predicting whatever you want them to do. And then they stream their outputs to subscribers, to them. It could be a UI, could be a third-party application like Uber. It could be storage. And so what we have developed is a mechanism for building applications on the fly, scaling applications on the fly for streaming data. Okay, I'm always asked, where does this stuff run? Is it edge compute? I want to answer that question by a very simple statement. The edge is not a place. Where do we compute? We compute where we can see the data, and the data is in the clear. And so where does the Pulsar broker run? Well, it runs wherever it can, wherever there is a CPU we can get it on, and ideally closer rather than further away from the raw data. And we compute wherever we can, often in the cloud, but perhaps sometimes towards the edge. Okay, so often we get deployed on Kubernetes. We'll find ourselves dealing with infrastructural components like Pulsar, and in the case of the telco provider that I mentioned earlier, we're dealing with a Pulsar implementation that scales to hundreds of nodes. All right, so we'll be deployed on Kubernetes. We deploy the same code in every instance. The instances just run on the JVM, but we don't depend on Java itself. And they form a mesh, a peer-to-peer mesh using WebSockets. Okay, and then they keep the web agents in sync on top of that mesh. So the graph of web agents, which represents a particular application, runs wherever we can, wherever we actually have access to data from the broker. If you happen to have lots of compute at the edge, you can just run at the edge. We really don't care. We're application layer stuff. So what I hope I've made clear is that Swim takes data from Pulsar broker, distributes that to web agents which run in a different address space, effectively the application layer address space, atop a cluster of peer-to-peer interconnected web instances of Swim. And these web agents can move around at runtime, and Swim indeed moves them. So Swim moves web agents closer to their raw data sources. It moves them closer to available compute and memory and of additional resources like GPUs. And so this model, this graph, which represents the application, is continuously in flux based on the resources that are available for running it. Okay, I'm going to summarize. Continuous intelligence is the business of analyzing, learning, and predicting from on the fly, not necessarily storing the raw data. Applications that we build like this always have the answer, and computation is driven by data, so they can react in real time. And in real time, what I mean is this. Every user in a city is interested in when their bus is approaching. You cannot tell the user when the bus has gone past, okay? So we have to react in real time at massive scale, and every web agent can do that. By doing this, we can compute 1 million times faster. And this is just Swim giving you back Moore's law, whereas REST in databases conveniently grows wide, but steals these benefits from you. So quick summary, that's the comparison of a snail and an F-18 in terms of performance. We get to use 90% less infrastructure. Everything stays in memory. And the applications are easy to deploy and develop, and we don't need complex DevOps-y approaches. We deploy the same code everywhere, and we simply deploy on top of something like Kubernetes. Once we have a running in-memory graph, we can directly connect it with something which allows us to do data science on live data. So perhaps PyTorch or whatever your preferred environment is. And once you've described found your key analytic that you want, you can push new analytics into the running graph, which will be continuously run for you. Okay, I'm going to stop right there. Thank you so much for your attention.